Okay, so when we were talking about covalent bonding, we're talking about a sharing of electrons, okay, between two non-metal atoms, okay? So it's always a non-metal with another non-metal. Okay, that's the basic idea. So when we say that what's the purpose of covalent bonding? The purpose of covalent bonding, similar to ionic bonding, is basically to get these atoms having a stable outer shell, okay, or what we say is a stable octet. To achieve an octet means we've achieved a state where the atom now has 8 electrons in its outermost shell, or in the case of helium, it's got 2 electrons in its outermost shell, okay? So that's basically what octet means. So if you see that word coming up anywhere, it just means to have 8 electrons in your outermost shell. Now, covalent bonding, similarly to ionic bonding, also occurs because of the electrostatic attraction. But now it's not the electrostatic attraction between the two different atoms, but rather the electrostatic attraction between the positively charged nucleus. Because what part of the atom exists within the nucleus that's positively charged, guys? What's the name that we give to that particle? Proton, excellent, okay? So between the positively charged protons that are in the nucleus of those non-metal atoms, as well as the negatively charged electrons that they're now sharing between them in that intersectional space, okay, or in that kind of like middle of that Venn diagram kind of representation there, okay? That is basically the electrostatic attraction that occurs, not the electrostatic attraction between the atoms, because we can't have an electrostatic attraction between the atoms here, remember, because both of the atoms are negative. They're both anions. There's no attraction between the atoms because they're not opposite to each other, as we saw with ionic bonding, where the atoms were oppositely charged, okay? But the electrostatic attraction still exists here, okay? Covalent bonds are actually very, very, very strong, okay? And that's because of this electrostatic attraction in terms of the fact that they're combining together and they are electrostatically attracting in terms of the positively charged proton and the negatively charged electrons there, okay? It's not like a charge where the two atoms are still separate or still relatively isolated from one another, which is kind of how we represent them in ionic bonding. So covalent bonds are strong, much stronger than your ionic bonds. So more stronger than the ionic bonds. And electron dot diagram. So this is what we were kind of looking at in the previous slide when we were drawing fluorine, and showing that and representing that. Okay, so that's how we would expect you guys to be able to draw it as well. In these two examples, again, these are just comparing the two. So you can see with the ionic bond, there's a clear kind of separation of those atoms there. We've got the metal cation kind of isolated, okay? It's not completely joined with chlorine. It's still isolated or still separate. And we can see that after sodium has given that one electron, it loses that electron completely. There's no mutual benefit or mutual sharing or a mutual exchange there. However, with covalent bonding, we know that because those electrons need to be shared between the atoms, they actually combine. They're almost like fused together. Okay, and we can see that because there's no gap between the atoms there, and we can see them both sharing that electron there. Remember that hydrogen by itself, okay, has an atomic number of 1, okay, and it's only got 1 electron. Now, is 1 electron stable? And how many electrons would we need in this case for hydrogen to become stable? Just put the answer in the chat box if you have an idea. So the question was, is having 1 electron in what is hydrogen's valence shell here, is that stable? And if not, how many would we need for it to become stable? Yeah, excellent, 2. Okay, we need 2 electrons to become stable. So that's why what happens is hydrogen is all here all by itself. Like, oh my God, I've only got 1 electron in my outermost shell. I'll never be stable. And then another hydrogen atom comes and it's like, you know what, I've got 1 too. Let's join, let's combine forces. And so basically when they combine together, you can see that they've now got 2 electrons in their outermost shell, and 2 electrons is stable, okay, for hydrogen, because hydrogen obviously only has 1 electron shell, and having 2 electrons in the first shell is stable. That's the maximum we can have according to what we learned in 3.5. Okay, so So that's basically what we're looking at when we're talking about hydrogen there. Okay, this is to form a hydrogen gas molecule as well. So the properties are a little bit different here compared to a single hydrogen atom. Okay, so that's basically covalent bonding. So covalent bonding has two nonmetals combining together. Okay, so covalent bonding, again, this is another example for you when we looked at this idea of the sharing of electrons between two nonmetal. And I think this is the example we did before when we were drawing it out, the two fluorine atoms, okay? And we said that a question, hydrogen atoms always covalently bonded? Yes, hydrogen atoms always, especially when we talk about hydrogen in the form of hydrogen gas always exists as a covalent molecule. And there are many other common substances that we encounter every day that actually are examples of covalent compounds. So another example is water, H2O. H2O is a covalently bonded molecule. We've also got carbon dioxide. Carbon dioxide is also an example of a covalently bonded molecule, okay? An example of a covalent compound, we would say. We'll look at examples of those as well. Okay, you can see here, or speaking of H2O, we've got it on this slide here, so I can show you guys this. So this is the covalent bond for H2O. Now, if we look at the formula H2O, can anyone tell me in the chat, just looking at the formula, how many atoms of hydrogen and how many atoms of oxygen do we have in that formula for water there? Yep, so we've got 3 atoms in total, 2 of which are hydrogen and 1 of which is oxygen. Excellent. Okay, and we can see that reflected here, guys. When we draw this as a covalent compound or a diagram there, what we see is that we've got 1 oxygen compound, and we know that oxygen has 6 electrons in its outermost shell. Okay, and so that means that it needs, if it's got 6 and we need 8 for stability, and we need 8 for stability, or 8 to make a stable atom, basically we need to join another 2 more. So what happens in this case of water is that 2 hydrogen atoms come in, okay? And the reason we need 2 is that if only 1 hydrogen atom came in, why wouldn't that work? Or why wouldn't that be correct? If we just got rid of this one, and we're like, we don't need you, second hydrogen atom, we just need 1. Why wouldn't that work in terms of ensuring stability there for the oxygen atom? Yeah, excellent. So obviously, if we only have 1 hydrogen atom joining and we take hydrogen's thing and we combine it there or whatever, there's only going to be 7 left. So we need 2 hydrogen atoms there. So we take 1 from here, 1 from here, and when they combine, so if I combine that there and that there, you see that the resulting diagram is this, okay? And I'm going to just highlight in a different color which ones were the shared electrons. So hydrogen came, there was already an electron here. This electron belongs to oxygen, but hydrogen came and connected its 1 electron here. That's the sharing electron. And this already existed. This one was belonging to oxygen, but hydrogen came along and shared its 1 electron here. And remember, it's not ionic bonding. Hydrogen is not just giving away its 1 electron. It's saying, you know what, I'm keeping my 1 electron, but I am going to share it with you. So this is a process where we mutually benefit. Okay, it's not just that you're taking my electron, we're going to share it together. And that's why you can see that the sharing also shows that they've kind of fused together. Okay, there's no kind of gap there. Okay, there's no gap that shows that these are 3 separate atoms. They have fused together, and they have to fuse together because when we actually write the chemical formula, that's a compound. Okay, that's not a separate, like 2 separate hydrogen and 1 separate oxygen. It was in the first bit of the diagram, but in the final diagram here, we can see that the bonds are there. We say that this makes 2 covalent bonds because we've got 2 atoms of hydrogen, 1, 2, that are actually sharing 1 pair of electrons each. So 1 electron here and 1 electron here. Okay, that's why we say it makes 2 covalent bonds. With this diagram here, we say this is a single pair. Okay, so it's only 1 pair there. So that's basically how do you know which elements can connect? Good question. So it depends on the compound you're given. Okay, so if you're given, for example, H2O, that's already a set formula. So you're just working with that. If you're given carbon dioxide, that's a set formula. So you know which compounds, or sorry, not compounds, which elements you'll have to work with and how many of those you'd have to draw. So in the case of H2O, we know that we have to draw 2 hydrogen and 1 oxygen. And when we find out what the valence electrons are for those elements in the compound, we can then decide, okay, which one is going to share it with something. Yeah, it's always going to be given to you, correct. Yeah, it's always going to be like, we'll give you a name of a compound, and then we are going to basically draw the compound based on that, okay, based on the formula you're given. And guys, speaking of that, there are prefixes that you need to know that give you an idea of how many atoms of a particular thing exist. For example, actually, wait, I'll go to the next slide and then that'll make a little more sense. Okay, before I talk about the prefixes, so I already talked about this at the beginning when I showed you the example of the fluorine atoms combining together. Okay, those are what we call as diatomic molecules. And we said that di means 2, okay? Di means 2. So that means that you've got a molecule that's made up of 2 atoms that are bonded together. We said that these can be the same atom in the case of chlorine and chlorine, or in the case of our example of fluorine and fluorine, or in the case of this example of hydrogen and hydrogen. However, they can also be different atoms, okay? But most of the time when we talk about diatomic molecules, at least in this spread, we look at them as being the same, okay? So in the case of hydrogen, when hydrogen combines with itself to form a covalent compound, which is hydrogen gas, that is one example of a diatomic molecule. Nitrogen gas is N2. Okay, remember I said all the gases exist as diatomic molecules. Fluorine gas is F2. Okay, oxygen gas is O2. That's because in one molecule of hydrogen gas, we have 2 hydrogen atoms that represent that. Okay, now there's a memory tip you can use to remember the different diatomic molecules. It's a little bit haram, but it's okay. It's have no fear of ice cold beer. Okay, so that's the memory tip. So you can remember it like that, or you can change the word beer into something a bit more permissible there. Okay, so that's basically what we call as a diatomic molecule. Okay, now there's no charge in a diatomic molecule because the total number of electrons and protons are the same. When we join them together to achieve stability, the number of protons in between this covalent diagram for chlorine is going to be the same as the number of electrons, which they have now also shared. Okay, so that's why diatomic molecules do not have a charge, okay, unlike ions that do have a charge. So the chlorine ion by itself, as we know, has a negative charge. However, when one chlorine combines with another chlorine, that negative charge no longer exists, because the main goal of this covalent bonding was to make things stable. And when we make things stable, no charge exists. Okay, if we're going to link this way back to a topic we learned, remember the last group of the periodic table are noble gases. What charge or what valency did we say that they have? Anyone can remember and put it in the chat. So our last group in the periodic table are noble gases. What valency or what charge did we say that they had? Okay, remember we say they had a 0 charge. We say they have a 0 charge because they're stable. They don't need to mix with the common elements or the common folk in order to become stable. They've got 8 electrons already in their outermost shell, and 2 in the case of helium. Okay. Similarly, when one chlorine ion or anion combines with another chlorine anion, they achieve stability. And that's why we say that they no longer have a charge. Okay, when they combine together as a couple or as a pair, they no longer have a charge in the same way that they did when they were a single atom, or sorry, a single ion. Any questions, guys, about diatomic molecules or anything on this slide here? All good? All right. You might be wondering what this means. That line, okay, H-H. Generally, when we have a covalent compound and we draw a diagram of it, if there's a single pair of electrons that are being shared, just a single pair, like 2 electrons, we put a single line. If there are 4 electrons being shared, we would represent it like this. Okay, if there was 4 electrons being shared. Okay, that means that there are 4 electrons or 2 pairs of electrons being shared. Okay, those are what we call a single bonds, double bonds, and triple bonds, which we'll talk about as well. Okay, so guys, the opposite of diatomic is monoatomic. Okay, monoatomic are just your single atoms. Okay, they basically exist as a single atom. So literally lithium by itself, chlorine by itself, before it joins and forms a couple with another nonmetal, that's known as a monoatomic molecule. Okay, mono meaning one. Alrighty, so we're almost done. I know it's a bit confusing, but just if you kind of get the basic idea so far, it's all right. We'll go through this again next week if we have to, maybe on Monday, if it's still a bit confusing. So as I said before, we've got single bonds, double bonds, and triple bonds. Now, if you've got 2 nonmetal atoms combining and they're sharing 2 pairs of electrons, as you can see here, if I just kind of highlight over that, here you've got 1, 2, 3, 4. In other words, 2 pairs of electrons that are being shared between these 2 oxygen atoms. That's why we represent it as O, 1 bond, 2 bond, O. That means that when oxygen forms oxygen gas, or the oxygen gas molecule, basically we've got 1 oxygen sharing 2 pairs of electrons with the other oxygen atom in order to become stable. Okay, how you see this happening, guys, is remember we said that oxygen has 1, 2, 3, 4, 5, 6 electrons. Let me just get rid of those scribbles. 1, 2, 3, 4, 5, 6 electrons in its outermost shell. And you can draw that out. That's what you're going to see. Okay, because remember we said oxygen has an atomic number of 8, which means that in its first shell, if you want me to draw the first shell here, it would have had 2 electrons. Yeah, so the remaining are 6. 1, 2, 3, 4, 5, 6. Okay, the other oxygen atom is the same. It's also got 6 electrons in its outermost shell. Individually by themselves, you can see that they're not stable. Okay, you can see that they've obviously only got 6. They need 8 to become stable. 8 is the goal. Okay, when they combine forces together and they kind of fuse together, they can actually share those 2 pairs of electrons. So 1 oxygen atom here, so oxygen atom A, shares its 2 electrons with oxygen atom B. Okay, and in doing that, they're sharing those 2 pairs of electrons, or in other words, the total 4 electrons there in the middle to make, sorry, let me get a different color. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and the other atom also has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's sharing those 4 in the middle. Those 4 belong to oxygen atom A, and those 4 also now belong to oxygen atom B. They are mutually sharing, or they are mutually benefiting from that covalent bonding. Okay, hopefully that makes sense. It's a little bit of a small diagram there, but I just wanted to show you how that worked. Okay, triple bond is the same concept, but in this case, we're now sharing 3 pairs. So you can see here 1 pair, 2 pair, and 3 pair. Okay, 3 pairs of atoms, or in total 6 total electrons are being shared. And guys, E minus is just the short form for electrons, as you would probably know. Okay, so that's basically sharing those 6 electrons there, and that is able to be stable as a result of that. Okay, because we know that nitrogen has an atomic number of 7. And this was actually a question on your practical as well, if you remember. So you've got 1, 2 in the first shell, and you've got 5 in the second shell. That's where the 1, 2, 3, 4, 5 comes from. And then the 1, 2, 3, 4, 5. So they're just sharing those 3 electrons in the middle, and that allows both of them to be stable. Okay, and I'll show you how quickly. If I can get a different color. So that's the 1, 2, plus the 6. 2 plus 6 is 8. Okay, and that's for nitrogen atom A. I don't know why I'm just calling it A and B, but just for the purpose of the example. 1, 2, and the 6 also belong to nitrogen atom B. So that is basically 1, 2 plus 6 is 8. So now this one has 8, this one has 8, due to the fact that they were mutually sharing those 8 electrons that were right in the middle. Okay, and we would represent this. How would we represent this, guys? In terms, oh, you can't draw, but how we would represent this. Can anyone tell me how many lines we would draw in between the 2 for a triple bond? Just put it in the chat box if you have an idea. So how many lines are we going to be drawing to represent that triple bond for the nitrogen molecule? Okay, I got my lines ready. If I get the answer, I can draw them out. Come on, guys. How many lines for a triple bond? It's really easy. It's in the name itself. Excellent. 3. Yes, 3. Okay, so 1, 2, 3. That's how we would represent that, okay, in terms of a symbol there. Okay, this basically means that nitrogen atom, sorry, change the color. Okay, this means that our first nitrogen atom, oh my God, it's still a line. Hold on. Okay, the first nitrogen atom shared 3 pairs of electrons with the second nitrogen atom. Okay, each of those lines means 1 pair, or in other words, 2 electrons. So if you've got 3 pairs, it's obviously 2 electrons times 3, which means 6 total electrons, which is what we see here. 1, 2, 3, 4, 5, 6. Does this kind of make sense, guys, so far? Do you understand the difference between what a double bond means and what a triple bond means? If you don't, let me know. All right, cool. Yeah, it's just think of the number, guys. 2 pairs means, pair means 2. So obviously 2 times 2 is 4. If it's a triple bond, it means you're going to be dealing with 6. So whatever bond you have, if it's a single bond, it's single. So 1 times 2. Double bond means double. So it's going to be 2 times 2. Triple means 3. So 3 times 2, which is 6. Okay. So just think of it that way. This is mostly like if we ask you this question in like a multiple choice or something like that. Okay, some more examples, guys, just showing you what that looks like. Again, all of these diatomic molecules, H2, O2, N2, as I said before, they exist as gas molecules. So you can see that kind of occurring here. I think we've already looked at these 3 examples on the previous slide, but this is a little bigger and a little clearer for you to see there. Okay, so here you can see that it's a single covalent bond because they're sharing 1 pair that is 2 electrons. Okay, so one from one hydrogen atom, the other from the other hydrogen atom, because we know that hydrogen has only 1 electron. It's got an atomic number of 1. Okay, oxygen is the same as we talked about in the previous slide as well. Oxygen is kind of sharing its 2 electrons from one atom and the other 2 from the other atom, okay, because it's got 6 electrons in its outermost shell there. So that's basically a double bond represented by the 2 lines. And then the triple bond, as we just talked about, is 3 pairs of electrons. So 1 pair here, the other pair here, and the other pair here. Okay, that's 3 pairs of electrons, which is why we show 3 lines like that, okay, to represent that. Now, guys, you might be thinking, okay, where is she getting all these electrons from? Why are there only 2 here? Why are there so many more here? Why is there even more here? It's all to do with the valence shell. Remember, I said this at the beginning as well. The word covalent bonding has the word valent in it. It's all about the valence shell. Okay, this is why I told you guys, if you don't know or if you can't identify how many electrons are in the valence shell of oxygen or hydrogen or nitrogen or whatever nonmetal you're dealing with, you are going to have a hard time with this topic. Okay, that's why I told you guys you need to understand 3.5 really well in order to be able to do this very well. They are literally connected, even though they're 2 different types of bonding. Your understanding of valence shells in 3.5 and how to draw them and how to identify the electrons in a valence shell of any element I give you is going to influence how you draw the covalent diagram. Okay, that's why I keep stressing about 3.5. Again, that's why I posted those videos on Schoolbox as well, for you to recap 3.5. Okay, so now you're like, oh my God, what's she going to talk about now? Molecular compounds. Don't stress. A molecular compound is just another word for a covalent compound. Okay, I don't know why we have 2 different words we use in your textbook, but a molecular compound is literally the same as a covalent compound, if I can type. Okay, now you might be thinking, oh my God, what's that diagram there? Why is she killing us today? It's not something you need to stress too much about. Okay, this planetary model of a water molecule, you don't need to worry about the word planetary model. Just understand that this is just showing you a water molecule. Okay, it's just showing you the water molecule for H2O, which we already looked at the first few slides in a more simple way. Okay, this is obviously our oxygen atom. This is our hydrogen atom. Okay, we know that that's our oxygen atom because we can see that it says, sorry, I'll rub this out. We can see this says 8p, 8n. Okay, 8p means 8 positive charge or 8 protons and 8 negative, which is the electrons there. So we know that this is our oxygen and we know that this is our hydrogen. Remember, I colored it in before in pink. So hydrogen is sharing one here and one here to make a H2O molecule or water molecule there. Okay, don't worry about the word planetary model, 3D model, structural model. Okay, just understand this basic idea. Okay, that this is what it looks like. And if I was to represent this as just symbols, I would write O, H, H. Okay, but I need to draw the electrons in a covalent diagram. So that's why they've been drawn here. Okay, and with this one, literally just understand that, you know, it's just again talking about the bonds. Okay, it's just written in a different way. We don't really do the dot diagrams as much, but it's just similar to the previous slide. So just remember the word molecular compound. Whenever you see the word molecular, it literally just means covalent. Okay, I'm really annoyed that the book uses two different terminologies, but it's literally the same concept. Okay, so that is the idea there. Okay, so now we're looking at the prefixes. So we're looking at how we name covalent, or in other words, how we name molecular compounds. Again, remembering and recapping that covalent compound is a nonmetal plus a nonmetal, okay? Always two nonmetals are combining together in covalent compounds or in covalent bonding there. Okay, so let's just show you guys what I mean by prefixes. Okay, so these are the prefixes. Okay, some of them you'll know, some of them are pretty straightforward. For example, mono we know means one. Okay, di means two. When we looked at diatomic molecules, you know di means two. Tri usually means three. Okay, tetra, that's probably one you'll have to learn. You might not just know that from your general knowledge. The tetra means four. Penta, you can remember, like a pentagon has 5 sides. That's how most people would remember that. So penta means 5. Hexa, again, hexagon has 6 sides, so hexa means 6. Hepta, heptagon has 7 sides, so hepta means 7. Octa, octagon has, if you know your shapes, then you'll be kind of good for this. Octa means 8, so octagon, obviously, and then nonagon, decagon. So if you remember some of your shapes and how many sides they have, the reason that the shapes are named that way is because of the number of sides that they have. Similarly, the prefixes that we use, like penta, hexa, hepta, octa, nona, deca, kind of correspond to our number of atoms that we need to have. So if I give you a formula, like for example, carbon dioxide, okay, we know that there's not an element called dioxide. We know that dioxide is something referring to oxygen, okay? So dioxide means we've got one element of carbon and we've got oxygen somewhere in there, and di means 2. So that means that we've got 2 oxygen atoms. Now, when we draw out, what's the formula for carbon dioxide, guys? Let me ask you a question and make you do some work now. Write it in the chat box. What is the formula for carbon dioxide? It should be general knowledge, I hope, by this point. CO2, excellent. Okay, so CO2 is our formula for carbon dioxide. Okay, you can clearly see that reflected. We've got 1 carbon, dioxide means 2 oxide, so 2 oxygen, so we've got 1, 2 oxygen. Okay, that's why the formula is written the way it is. Okay, if I say carbon monoxide, which we'll learn a little bit more about in the next chapter, can anyone guess what is the chemical formula for carbon monoxide? Looking at the word mono, we know oxygen is involved. What does the word mono mean? What number do we correspond it to? 1, excellent, okay? So we correspond it to the number 1. So because we don't write the number 1 in chemical formulas, remember, so all we're gonna write, guys, is CO. Okay, we don't write COO1. We say we usually pretend the 1 doesn't exist there. We write CO, and that is the formula for carbon monoxide. Okay, so you can see, even though they look similar and they sound kind of similar, because of the different prefixes that these two covalent compounds have, the number of oxygen atoms that exist in the chemical formula are different as well. Okay, and if we were to ask you to draw this out, you would have 2 oxygen atoms happening in this one, but only 1 oxygen atom happening in carbon monoxide, or occurring in carbon monoxide there. Okay, so the prefixes are there, guys, for you to understand what that kind of looks like. Okay, so that's basically what we talk about when we talk about the rules, okay, for naming. Now, it's not just about naming. So when you guys start your worksheet for 3.6, what you're going to realize is that you need to be able to look at the name of that compound with the prefixes and understand, using the prefixes that are given, how many atoms of a particular element will be given to you. So if I just open up your worksheet and maybe ask you guys one question from it, let's look at a hard one here. Oh, this one looks good. Okay, let me do that one and challenge you guys today. Okay, so I'm going to write it down. So phosphorus trifluoride. Okay, now I want you guys to tell me in the chat box. You can use your periodic table. You can use your periodic table if you want to, but how many atoms of phosphorus and how many atoms of fluoride are we going to have in the chemical formula for phosphorus trifluoride? And then we're going to write this chemical formula together. So looking at the word itself, looking at the prefix, we only have one prefix, which is tri. Match that to what the prefix, what number of atoms that prefix represents, and tell me how many atoms of phosphorus and how many atoms of fluoride will exist in the covalent compound that's called phosphorus trifluoride. Excellent. Yes, 3. So 3 fluoride and 1 phosphorus. Excellent. Great work, guys. So that means that we're going to have, when I draw this out, you're going to have 1 phosphorus, so we can write 1p, and 3 fluoride, okay? And we know that because we look at the prefix that's attached to the word fluoride, okay? And if we were going to draw this out, it would literally be p in the middle, and then you'd have the 3 fluoride around it, okay? And this is a really bad drawing, but yeah, you get the point, okay? And then we just show that they're sharing the electrons there. So that's the basic idea. Now, there are some rules when you write this out or when you draw this out, okay? And the basic idea is that, you know, when we're talking, to write the 1. No, you don't need to write the 1, okay? Usually if there's a 1 there, you just pretend that it doesn't exist. So yeah, the most metallic nonmetal element will be written first, and the one that's more non-metallic, which means the one that's a little bit further right onto the periodic table, is going to be written last. Okay, if you look at your periodic table now, if you've got it in front of you in your hands or whatever, if you look at the periodic table, you'll see that phosphorus is actually located in group 15, which makes it a little bit closer to our metals. It's more to the left-hand side of the periodic table compared to fluorine, which is actually in group 17, which is a little more to the right of the periodic table. If you have that open in front of you, you can understand that that's why we wrote that formula, or we wrote the chemical formula as, and let me write it again. That's why the chemical formula was written like this, rather than, let me write another one, rather than this. Did I spell it? Okay, basically this, look what I've done. Okay, hold on, let me write that again in a space that's actually correct. Okay, trifluoride phosphorus. Okay, so that's basically why this rule, that the most metallic nonmetal, or the nonmetal that's furthest left of the periodic table compared to the other one in the compound, is always written first, okay? That's why this is correct, because phosphorus is actually a little bit closer or a little bit more to the left of the periodic table. It's in group 15, whereas fluorine is in group 17. This is why this is correct in terms of our naming notation and naming rules there, okay? And this is why this is wrong. Okay, it can't be trifluoride phosphorus because fluoride is further to the right of the periodic table. We say it's more non-metallic because of that, okay? And we say that for that reason, it should always be written last, okay? That's why this formula is correct and that one is wrong, okay? To give you guys another example, nitrous dioxide is basically nitrogen and one nitrogen atom and 2 oxygen atoms because of dioxide, okay? We don't write nitrogen dioxide as O2N. We write it as NO2. That's because nitrogen is again in group 15. It's a little bit more further left to the periodic table. It's a bit closer to our metals on the left-hand side. And oxygen is obviously in group 16, which means it's very slightly closer to the right-hand side of the periodic table. Basically, whichever non-metal comes earlier in terms of an earlier group, and is less towards the end, that one will basically be written first when you write your chemical formula, okay? And we already talked about how some compounds end in "ide," okay, chloride, fluoride, dioxide, okay, all of those things. What else do I need to tell you guys from this slide? Yeah, so we already talked about how we can use the prefixes to tell us the quantity of each element or each atom in that compound. Yeah, okay, this is one thing. You need to memorize the prefixes. Okay, like I said before, there shouldn't be a big deal when it comes to memorizing the prefixes, simply because some of them just correspond to your shapes that you've learned in maths. The only really one you'd need to learn is tetra. Tetra meaning 4. Look, I'm not really like, I know the basic shapes, but I don't know like every shape in the world. So maybe there's a shape that corresponds to tetra that you could use to remember it, but that's probably the only one you need to know. Okay, so that's basically our prefixes. You do need to memorize them. Okay, alrighty, so okay, I know you guys are probably drained. Okay, I know this isn't our last lesson of chemistry and I'm teaching like I'm gonna like die tomorrow or something, but no, I know, but 3.6 is hard. Okay, that's why I'm trying to get through it in one go, because if you don't get through it in one stretch, you're gonna forget everything. So that's why I'm going to let you guys go. I'm not gonna go to 12:40, I promise. Okay, we're almost done. So these are just some examples of names, guys, from the previous slide, just to show you again more examples. Okay, so we've got, you know, nitrogen monoxide, 1 oxygen, dioxide, 2 oxygen, trioxide, 3 oxygen. Okay, sometimes you have both elements. So in this case, for example, we got dinitrogen pentoxide. Okay, so dinitrogen means 2 nitrogen, pentagon has 5 sides, so that means 5 atoms of oxygen. Okay, if we were to give you in a multiple choice question something like let's say this one, iodine, if we were to give you this symbol and as a multiple choice question ask you what would be the name of the compound or molecular covalent compound represented by IF7, you need to kind of use your understanding of the prefixes that you've memorized and understand that, okay, a heptagon usually has 7 sides. Okay, so that means heptafluorine means 7 fluorine atoms and 1 iodine atom. So it should be iodine heptafluoride, and you'd select that option as the correct one. Okay, that's basically just some examples for you there. Okay. Right, and we already talked about the rules for naming in the previous slide. Just some general properties of covalent compounds, which we already discussed as well in the beginning. Molecular compounds or covalent compounds don't conduct electricity. They are actually stronger. The bonds between them, between the nonmetals that are in a covalent compound, are stronger than the bonds between, than the ionic bonds between a metal and nonmetal in ionic bonding. Okay. Another property of molecular compounds is that they don't, is that they're flammable. Okay, which is why methane gas, for example, methane is an example of your covalent compound. Okay, it's made up of 1 carbon atom and 4 hydrogen atoms. Okay, so CH4 is the formula for that. So those are some properties of molecular compounds. Learn at least 3, but have a general understanding of all of them. But maybe for the test, just learn about 3. There should be enough. Okay, again, I've already compared ionic and covalent bonding in the beginning when we did our little drawing. But this is the basic idea, guys. Okay, so yeah, ionic bonding is metal versus non-metal, and covalent bonding is a non-metal versus another non-metal there. This is just a summary of key concepts that you can again go through, but just remembering covalent bonding is the bonding between 2 non-metals, okay, in order for both of them to mutually benefit. How do they mutually benefit? They mutually benefit by sharing those electrons in that intersection or that middle joining point there where they join or fuse together. And basically what that leads to is that both atoms involved in that bonding become stable. Okay, their outer shell becomes stable. We're only focusing on the outer shell, which is the last shell of valence electrons in covalent bonding. We're not really too worried about what's happening in the first or second shell, only what's happening in the last shell there. Okay, yeah, that's it for 3.6. Okay, so I'm going to stop the recording here.